Welcome back, guys. We are going to keep talking about counting. That's what we're on. And we just finished talking about permutations. And I want to bring up another type of situation or concept, and that's known as combinations. So what's the big difference between a permutation and a combination? Well, it really speaks to order. Do I care about the order or not? So let's look at this. So let's say that there are 40 people that are called in to fill a jury, a 12-person jury. How many different juries are possible? Well, that's going to be a surprisingly large number. But what I want to get at is this. You have a jury, and people are seated in their seats, right? And there's 12 seats. If the people stand up and change seats, same 12 people, but they rearrange themselves, is it a different jury? No, it's not. So really, I don't care what order people are chosen to be in the jury. I only care about who is in the jury. So I don't want to count the case where I'm picked and then you're picked, separate from the case when you're picked, then I'm picked. The order that you're picked doesn't matter, simply who's on the jury. There are state lotteries played this way as well. You'll have a scratcher or something, and there'll be 5 numbers that are generated, and you don't have to have those 5 numbers in any particular order. You just have to have those 5 numbers. It's another example of a combination, okay? And so a combination, as a definition, is just a set of objects independent of order. So some examples, we mentioned a jury. There are some lotteries. How about a class? Right? If you come into class and sit down with your classmates, and then tomorrow you come back into class and you all sit in a different seat, are you still the same class? Of course you are. The arrangement that you're in doesn't matter. A family is sitting around a dinner table. Do families still do that? Mine does. A very, very nice part of the day. I'm on a tangent. A family is sitting around its dinner table. They change where they're seated. It's still the same family, right? It's not 2 different families all of a sudden. It's the same family. That's the notion of a combination. The order doesn't matter. If you remember the horse problem, right? How many ways can horses finish first, second, third in a 15-horse race? Well, what if we modified that a little bit? And I said, okay, I own 3 horses. How many different ways can my horses finish first, second, third? I don't care which of my horses is first, second, third. I just care that they're first, second, third, okay? That's also a combination. So here's the formula. The number of n objects chosen r at a time is given by this. Well, you might recall the permutation formula. Right? So it's almost like this combination formula is the permutation divided by r factorial. It's another way of looking at it. Okay, let's take this apart. So, because again, this is not one of those formulas that you look at and you go, oh yeah, that just makes sense. No. So let's start simple. Let's say that I have letters A, B, C, D, and I want combinations of 2. Okay, I want combinations of 2. Well, I could do AB, AC, AD. I could pick BA, BC, BD. I could pick CA, CB, CD. I could pick DA, DB, and DC. Now, are there any that I missed? You might pause and ask yourself, are there any other pairs that I could build? Yeah, that's all of them. So if I were to ask about permutations, right, there'd be 3, 6, 9, 12 different permutations. But if I don't care about the order, right, all I care is what 2 letters are in my pair, not the order that I get them. Okay, almost thinking about it like drawing, like you're playing blackjack or something. You get 2 cards. You have those 2 cards in your hand. You change the order of them. It's still the same hand, right? You haven't changed your hand. So I don't care about the order. I just care about what's there. So when I look at AB, I am not going to count AB and BA. AB and BA are the same to me. Similarly, AC and CA are the same. AD and DA are the same. I'm not going to count BC and CB. If I get BC, I'm going to count CB as the same. BD, DB, CD, and DC. So really, we only have, well, 1, 2, 3, 4, 5, 6 combinations. Okay? If you want to use the formula that we have up here, well, I'm saying C, and then, whoops, not 6. I've got 4 objects, right? And I'm choosing 2 of them. And so I have 4 factorial over 2 factorial for minus 2 factorial. So I've got 4 times 3 times 2 times 1 over 2 times 1 times, and then 4 minus 2 is 2. So 2 times 1. Well, look, 2 times 2 is 4. So there's my 6 combinations, okay? So how do you distinguish between a combination and a permutation? You need to ask yourself, is the order important? Is the order relevant, okay? Here's an example. 200 students are in a lottery to be part of a 30-student research group. How many different groups are possible? Well, this is a combination because I don't care about the order that the students are picked. I only care about who is picked. So I've got 200, comma, 30. And so this will be 200 factorial over 30 factorial times 200 minus 30 factorial. So we have 30 factorial, 170 factorial. All right. And then here, right, you really want to take advantage of some type of computation aid. I'll show you what it would look like on a calculator. So, and I'm totally fine with using calculators. And let's see here. So here's this one. And so this has the option of picking, of doing these. So it's under the math menu on this. I know you don't have this calculator, but I will show you also how to find one of your own. It's this NCR. And so you would just type 200, 30, and there we go. 4.09681705. Let's see. We get, sorry, I want to write this down here. Okay, someone's car is honking. I apologize for that. All right, here we go. We've got, so 4.0968. I'm going to write this down in all of its glory here. 1705 times 10 to the 35th. That's a huge number. This is really, if I wanted to write it all out and not in scientific notation, it would look like this. It would be, why is that not working? Okay, we would have 4 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There'd be like 35 different places here. Okay. Quite a lot. So scientific notation, it's a nice way to write things. All right, let's look at the next one. How many 5-card poker hands contain 3 aces and 2 kings? Well, there are 2 things at play here. We've got, first of all, the number of ways to get 3 aces times, right? This is the fundamental counting principle. Number of ways one event can occur times the number of ways another event can occur. So times the number of ways to get 2 kings. Well, let's think about it. Do I care what order those aces show up in my hand? No, I don't care. In fact, if you've ever played cards, after you're dealt your hand, what do you usually do with it? Yeah, you rearrange, right? So how many aces are in a deck? There are 4. I want 3 of them. So this is 4, 3. How many combinations of 3 aces can I get from 4? Times, and then there are 4 kings. How many combinations of 2 kings can I get from those 4? And so I've got my 4 factorial all over 3 factorial times 4 minus 3 factorial, which is 1 factorial, times 4 factorial over 2 factorial, 2 factorial. Okay. Well, 4 factorial over 3 factorial. The 3 factorial is going to cancel with the 3 times 2 times 1 in the 4 factorial, leaving you with just 4. And then let's see, over here, 4 times 3 times 2 times 1 over 2 times 1 times 2 times 1. 2 times 2 is 4, so those cancel. So you got 4 times 6, 24. So there are 24 different 5-card poker hands that will have 3 aces and 2 kings. Okay, again, notice I'm not caring about the order. Computationally, we've just got this additional term in our denominator, right? We're dividing out those instances where they got the same objects in different orders. Okay, so let's go back to our motivation problem now. 40 people, 12-person jury. 40 people, 12-person jury. People to fill a 12-person jury. Well, again, we don't care about the order that the people are selected for the jury. We only care about who's in the jury. You have a jury and you sit in different seats, it's the same jury, right? So we have a combination. And we know this is equal to 40 factorial over 12 factorial times 40 minus 12 factorial, which equals 40 factorial over 12 factorial times 28 factorial. And when you do that in all of its glory, you might be surprised. Sorry. So 40, 12, 5, 5, 8, 6, 8, 5, 3, 4, 8, 0, 8, 5, 3, 4, 8, 0. So what is that? Almost 5.6 billion? Think about that. Picture yourself in a room with 40 people. That's something we can relate to, right? You're sitting around, you're in a class, there's 40 people. You know what that feels like. You know what 12 people feels like, right? You get picked with 11 of your classmates. But from that class of 40, from that pool of 40, it's possible to get almost 5.6 billion different groups of 12. That's a whole lot of juries you can get from just 40 people. It's one of the reasons it's pretty easy to see if a jury's been tampered with, right? If you've got a guy that is on trial and maybe 5 of his buddies make it onto a jury, you ask yourself, what's the probability that that happens? When there's 5.6 billion different options, that's a very small chance. So odds are it wasn't random. And if it wasn't random, you got trouble. So it's amazing how these numbers blow up and defy all intuition. I mean, I don't think anybody would have guessed a number this big right off the bat. But that's what it is, okay? It's very mind-boggling. Which is why when we started this discussion about counting, I mentioned counting is so basic. You know, you point 1, 2, 3, 4, but as a science, it gets very, very technical because there are astronomically large numbers that come up when we're starting to talk about counting combinations and permutations and things. Okay, so the big idea right now is for you to be one, familiar with the notation, and then also able to use a calculator or whatever tool you have to compute these, and then to be able to discern which is appropriate counting technique, permutation versus combination. Okay, eventually we're going to put these all together and look at some more compound events and so forth. So this is an important topic. This comes up a lot. In fact, you need it to do probability. So you'll see this kind of behind the scenes eventually when you're doing probability. For now, we just want to get used to counting and these different techniques. So with that, I will leave you and see you soon. Bye, everybody.